So hello, today we're going to discuss differential amplifier. Rather, I will explain how to solve different kind of problem in differential amplifier. So this is the first problem that how you will solve the differential amplifier. This differential amplifier differential gain. So differential gain nothing but V out by differential input difference. Okay, so how you can find that? So one technique to solve this problem is to find the model of all the transistor and then replace the model and solve KCL and KVL equation. This could be a lengthy equation, or you can do another process like try to find the symmetric point or symmetricity in the circuit. So this point will be AC ground. Now why this is AC ground? Suppose these are two differential inputs. Suppose this is Vn by 2 and this is minus Vn by 2. So as it is Vn by 2, so it will suppose the input is like this. So for this the output will be same as the input, and in this case the output will be opposite. And if you add this to this will be constant value. So in AC analysis this will be AC ground. So this is AC ground, and suppose the dimension like W by L ratio of M3 and M4 are same, and W by L ratio of M1 and M2 are same. So to make the circuit symmetric, what we do, we just change the way that we can write R1. So instead of writing R1, we can replace R1 like this: series combination of two resistance R1 by 2 and R1 by 2, and this point will be also a virtual ground, because if this point voltage is plus V, this point voltage will be minus V. Now let's prove what is the voltage of this point. Suppose this is Vx. Okay, now if we apply KCL at the node, this node A, then what we can write, like Vx minus V by R1 by 2 plus Vx plus V by R1 by 2 is equal to 0. So from this we can write Vx equal to 0 volt. So this is also will be a virtual ground. Now if I modify the circuit will be look as this. I am drawing the AC equivalent circuit. Okay, and the M3 and M4 are in diode connected device configuration. As we all know, the impedance, output impedance of the diode connected device is nothing but 1 by GM. Okay, so now just replace the circuit like this: R1 by 2, this is virtual ground, R1 by 2, and this part, and as I told earlier, this point is a virtual ground, so replace this as a ground, and this two part, in 1, in 2, and you can see the whole circuit is symmetric with respect to this axis. So calculating overall gain, differential gain of this circuit and calculating gain of a single side will give us the same result. Okay, so we does not need to calculate the gain of the overall circuit. So you can just replace the circuit as this. Suppose this is Vin, and I replace the diode connected device with this output impedance, which is nothing but 1 by GM. So let me write 1 by GM3 in this case. So it is 1 by GM3, and with parallel this resistance R1 by 2. Okay, and this is V out. So this is basically a common source topology, so we can easily find the gain, and the gain is basically minus time GM into R out. So here it is minus GM1, R out means 1 by GM3 in parallel with R1 by 2. So this is the overall gain of the circuit. Like this is the overall differential gain of the circuit. So differential gain is basically if you apply differential input, uh, then the gain that you got in the output V1 V2. So actually the differential gain you can write as V1 minus V2 by V in 1 minus V in 2. And another type of gain is common mode gain. In that case you apply in same input in both this M1 and M2 and then calculate the output. So in the ideal case, in that case the gain should be 0, right? So this is another topic I will discuss later. Now let's look at the next problem. So this is also a symmetrical circuit, as you can see from this axis, and this point is the AC ground. Okay, this point might have some DC bias, but for AC value there will be no change. There will be no change in its AC fluctuation, uh, because some DC value will be there. To operate this circuit, we need to give some VDS to this transistor M5, otherwise it will not operate. So some DC value is present, but that DC value is constant. Okay, so you can make the circuit symmetric in this way. Now our task is to find the output impedance of this structure. Okay, so this is a common structure, like for NMOS. I am showing the calculation for NMOS. For both NMOS and PMOS, the calculation will be same. Okay, so suppose this is a circuit and we looking in from this, from drain. So what will be the output impedance? Okay, so let's try to find in an intuitive way. So what we do, we replace arrow here, and to connect to find the value of R out, we will connect a test voltage and find Vx and Ix result. So let me erase this. So this is Vx and this is Ix. So if I can find Vx by Ix, then I will get R out, right? Total resistance offered by this structure. So this resistance will be same as this. So this current is Ix. So this Ix current also flowing here. So what is the total amount of voltage drop here? R1 into Ix, and gate voltage is 0. So what is the value of VGS? 0 minus Ix R1, 1 minus Ix R1. So what is the current flowing through here? Gm times VGS minus Gm Ix R1. So what is the amount of current that flowing through R naught? It is nothing but IR naught Ix minus Gm VGS, so which will be Gm Ix R1. So that takes Ix as common, 1 plus Gm R1. Now we get this current IRO. Now if we apply KVL in this loop, then what we can write? Like Vx is equal to IRO into RO, that means Ix 1 plus Gm R1 into R naught plus Ix R1. So Vx by Ix is equal to 1 plus Gm RO into R1 plus R naught. So approximately its value will be Gm RO times R naught. So this resistance value will be Gm3 RO3 R1. Okay. Now if I modify the circuit will be basically look like this. This is AC ground, and this resistance will be replaced by Gm3 RO3 and R1, and this is V in, this is my V out. So now the overall differential gain of the circuit will be minus Gm1 Gm3 RO3 R1. So in this way you can easily write what is the voltage gain or differential voltage gain of this type of differential amplifier. One thing you must do before coming to this topic, you must know how to find the gain of this, like common source, common drain, common gate. So if you remember those formula or know how to do this, then it will be easy for you. Otherwise later some big circuit will come. If you go for deriving in each and every circuit, it will be difficult for you, right? So now let's go to the next problem. So this is a similar kind of problem that I solved earlier. So yes, so here what is the difference? Here the load is a direct connected device, or here the load is a current source. So the current source, so if you look in the current source like this, suppose VB here, if you see what is the output impedance, what would you see? So for calculating the output impedance, you make this voltage source as 0. So this VGS is 0, that means no current flow through here, all the current is flowing through R naught. Okay, so the R out is basically R naught here, right? And which is a very high value, which is basically a very high value. Now you can easily solve the problem. So what do we do? you connect two R1 by 2 resistance in series to make R1 and just draw the line of symmetry and solve the problem. So this is basically the circuit basically becomes like this is the ground, and this point is AC ground as I already told, and this M3 can be replaced as by the resistance RO3, and this can be divided into the series connection of 2R1 by 2. So this is my final circuit. This is V in and this is V out. And what will be the gain? The gain of the circuit will be minus GM1, this is M1 minus GM1 RO3 in parallel with R1 by 2. And if you want to consider the RO of this resistance, then you can also consider like RO1. So typically the value of this RO is basically 1 by lambda ID. Okay, this RO value is very high as compared to R1 by 2. So you can write GM1 is R1 by 2. As we know, the if some resistance connected in parallel, the equivalent resistance is less than the smallest resistance which we are connected in parallel. So in this way you can easily solve this problem, and this is another problem. So this point, from this point you can divide the circuit and calculate the gain. Now this is the homework you can do. Now let's go to the next problem. Okay, this problem we need to calculate. Our task is simple, right? We have to first calculate the output impedance of this structure. So you can similarly make similar kind of NMOS structure of this. Okay, like R1 connected here, need to calculate Vx by Ix. So if this node voltage is Vx, this node voltage is also Vx because gate current is 0. So the VGS value is Vx and this is R0. Now what is the current flowing through here? This is nothing but Gm times VGS. So this is Gm Vx. So total current that flowing through R0 will be nothing but Ix minus Gm Vx. Now if we apply KVL in this loop, you can easily write Vx equal to Ix R1 plus R0 Ix minus Gm Vx. So now just take Vx as common. This will be 1 plus GMRO. If you take Ix common, this comes as R1 plus R0. So Vx by Ix is equal to RO plus RO, I1 plus GM RO. So I am writing this as R out. Now you need to calculate the gain. This is the ground and this is basically a common source amplifier. The gain will be nothing but minus GM times R out, or you can write as R out parallel RO1. So you get the differential gain of this differential structure. So this is the last problem. Okay, I think you understand what I am trying to say. So in this type of problem, just try to find the symmetricity of the circuit. If there is no symmetricity, then you can go for drawing the model of each and every transistor and solving the problem. but most of the cases the circuit are symmetric. So I hope you understand like how to solve this problem. So this is basically try to you must know the what is the gain of this, like common source amplifier gain, which is GMRD, common gate, and common drain amplifier gain. So it will be very helpful for you when you are solving this kind of big circuit, or later more bigger circuit coming with respect to this. So thank you for watching this video.